Welcome or welcome back to Why This Universe, and Happy New Year. 2025 is set to be an exciting year for cosmology, so to help celebrate the new year, we're going to be talking about what exciting results you should be on the lookout for this coming year. And we have a very special guest here to help us do that, so stick around. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper. So on January 1st of this year, I was scrolling through Twitter or X, whatever you want to call it, and I noticed a thread by my friend and colleague Dan Scolnic. The thread that I found laid out what he called the top papers in cosmology that he's looking forward to in 2025. So to start out this year, I thought it would be great to have Dan on this podcast to walk us through this list and tell us about some of these potentially very exciting developments we might hope to see this year. So Dan's a professor at Duke University, and before that, he was a postdoc at University of Chicago, where I got to know him. He worked in the dark energy survey there and continues to work on that as well. But he works on a lot of different things in cosmology. He's probably best known for his work on measuring the universe's expansion rate, what we call the Hubble constant. But of course, his publication record covers a lot more ground than that. I would describe him as an expert in all things near-field cosmology, or the kind of cosmology that's done by observing things within the surrounding, 10, 20, 30 billion light years or so. Thank you, Dan, for coming on Why This Universe.
Thanks for having me. Also, I'll just say I'm a big fan of your podcast. And I listen to it before I give my intro to astronomy lecture to make sure I understand all the concepts that I'm about to talk about.
Oh, that's
educating future generations. Great. Thanks, Dan.
I mean, I honestly listened back to some of ours too, and I'm like, I feel like I forgot about this.
Yeah, if I knew all the things that I had forgotten, I'd be pretty smart.
Yeah. Like one thing I remember is like you're talking about how brown dwarfs are not brown, and for some reason I never learned that, and that has just stuck with me.
I didn't know that right now, so apparently that's one of the things I forgot.
I swear it's you who said it.
All right. So before we jump into your list, Dan, let's set up the situation a little bit by talking about the Hubble tension. So maybe just in your own words, can you explain what the Hubble tension is, like what this is all about?
Right. So my team and a number of other teams in kind of what you would phrase as near-field cosmology, we tried to measure the expansion rate of the universe locally. So we look at nearby galaxies and we measure the redshifts of these galaxies, we measure the distances of these galaxies, and we compare the two. And from that, you could measure how fast the universe appears to be expanding today. And typically, teams, when they do this, they get a number around what we call H naught of 73 or so, and it's in kilometers per second per megaparsec. Now,
so H naught, this Hubble rate is like a number that tells you how fast we're expanding today, and in these units, and like let's not worry about what the units mean.
Okay,
a number like 73, right?
A number like 73, right. Exactly.
Okay.
Now, when other teams go and they take pictures of the universe when it's very young, like from the time of the cosmic microwave background, and they can measure this really exquisite picture of what the universe looks like and how far away things are in the universe when it's very young. And then they use what we call our standard model of cosmology, basically everything that we think we understand about cosmology, and they make a prediction of how fast the universe should be expanding today. And when they do that, they predict the universe should be expanding at a number of like 67, so not 73. And
kind of close.
Close. And closer than the times in the past when people have compared, but kind of within the uncertainties of how well we can measure this, it's now crossed whatever threshold people have of this is a serious problem.
Yeah. The quoted error bars are much smaller than this difference of 67 to 73. And like you said, it's changed a lot in like our lifetimes. Like when I was in college, my textbook said, well, the Hubble constant could be 50 in these units or 100. We're not really sure. Now we're arguing like pretty intensely about 67 versus 73. So progress, I suppose.
Absolutely. And there was this famous time, it's called the Hubble Wars, where there's this argument between 50 versus 100. And I think we understand kind of the mistakes both sides were making, but I'd still say the ghosts of those measurements still very much haunt us today. When people say, well, I remember when it was 50 versus 100. Why is this a big deal of 67 versus 73?
Yeah, I bet you're frustrated by this, Dan, working in the field you do. But, I think if you went to a big cosmology meeting or something and just like asked around, people would mostly think that in the end, this will resolve one way or the other by some systematic uncertainty or something kind of mundane that people are doing wrong and don't know about yet. And it will shift one way or the other, maybe meet in the middle. But what's your view? Like, do you think that's likely? Do you think it's more likely that something more, foundational is at stake here?
Right. Yeah, I would say that I've tried really hard to let the data speak for itself. And 4 or 5 years ago, I thought maybe there's a chance that things meet in the middle. And absolutely, I hear from lots of people in the community like, oh, we know how this story will end. And now I feel like I've seen enough measurements and the data is so strong that I think this thing is real and I think this thing is foundational. And it would be, there's nothing I hear on the horizon that would convince me otherwise.
So when you say that, do you mean foundational in the sense that these two ways of getting this number are both right in their own way, and we're missing something about the model that connects them?
That's exactly how I feel. There's been so many cross checks at this point that I think these numbers are set, and it's not the measurements are wrong. It's some other piece of the story, possibly our model itself.
Yeah. So the standard model of cosmology that we teach in our textbooks and our classes today, there's something wrong in that, subtly wrong, but something wrong. Yeah. So what are ways in which we might, give the listener a feel for like what kind of things you might have to introduce or change in the standard model of cosmology to kind of reconcile these two different seemingly discrepant measurements? Right.
So there's kind of 3 places to look generally. So we have this measurement of the universe when it's very young. We have the measurement of the universe today. And then we have that kind of model that describes everything in the middle. So if you're going to try to find a solution, you either have to do it when the universe is very young, something about how the universe changes, or something unique about our place today. And all types of these solutions have been proposed. In terms of something happening today, there's a number of papers that are saying, well, we live in a very special place in the universe, something that is just different about where we are compared to the kind of homogeneous universe that is foundational to our understanding of astronomy. I personally feel like it's never good to think that there's something special about us. That's never worked well in the history of astronomy, but it's still being proposed. At some level, we have to be a little special, right? I mean, one way or the other, right? The universe isn't perfectly homogeneous, right?
And every era of cosmology is special in its own way.
Thanks. We're all special. I do agree with that. Yes, right. But this would have to be actually quite special, and that seems hard to accept. But also, the data that we have about where we are, there's nothing else we're seeing that seems like we're that special.
Right.
So then if you go to the early universe, then there's a number of really interesting theories. There's like changing what we understand about neutrinos, or adding in what's now getting a little bit popular called early dark energy, that there's another type of dark energy besides the one that's making the universe accelerate now that popped up and kind of disappeared at this rather specific time. And that would be the right type of thing to explain this. And then the middle area is kind of really pushing something big about our foundational model, that there's something about dark energy itself, or dark matter, or gravity, that needs a kind of fundamental rethinking. And I'd say up till a year ago, that wasn't really on the table. And then there have been results in the last year that I think are opening people up to that being a possibility as well.
All right, so after setting the table that way, let's go to our list, okay, or your list. So the first one, we're going to need some unpacking here, but the first one on the list is that there will be new measurements of the Hubble constant from the James Webb Space Telescope, JWST, TGRB-SBF project, which could be announced as early as this month. Tell us what that is.
Right. So this is a team that is using a way of understanding how far away galaxies are, look at specific property of stars. TRGB means the tip of the red giant branch. So stars, as they evolve, they hit this time in their sequence where their luminosity is roughly the same. And when a luminosity is the same, you could use them as what we call a standard candle, a way of saying, hey, we know how luminous this is, so if we measure brightness, then we can figure out how far away this galaxy is. And this is a new team that will be using new JWST data and kind of doing this totally independently. And this ties into a bit of I'd say kind of like drama on the local side of the team that I'm a part of. It's called the Shoes team, and we use JWST data to measure the expansion rate. And there's another team also kind of probably based out of Chicago called CCHP, and they seem to say that maybe they get slightly different values of the Hubble constant than we get. So having a third team is just very important to kind of making sure everyone's on the same page.
So I'll just add that we had Wendy Friedman on this podcast way back in episode 41, and she's part of that University of Chicago team doing this stuff. I don't think that data was available at the time of that episode yet, though. So this is more recent than what you're talking about. Yeah.
Right. Yeah. So they've had a bit of a strange history where last year they announced that they were getting possibly lower values of the Hubble constant, but then a paper didn't come out. And then they do a few different techniques, but they still haven't released the data or the two of the three papers. So I think we're kind of all waiting to see what the numbers come out as. But having this third team, I think, is just kind of really important for making sure everyone understands.
Do the memberships of any of these teams overlap at all, or are these completely different independent groups of scientists?
Well, for the team that I'm on, we actually have some people who have kind of moved between teams. And from this new team, this third team, there's a little bit of overlap. And then CCHP, I think, is pretty internal in their team.
Okay. All right. So how big a deal would it be if this third team comes up with a number of, 71, 72, 73, 74?
Right. So I think it would be a pretty big deal in that, to me, it would just kind of be case closed on the local side that the value of the Hubble constant is above 70. Because so our Shoes team, we combined our data with the CCHP data. We think it's already fairly convincing that H naught is high, but having this third team will really settle it in the eyes of the community. So I think I feel a specific way about how things are looking, but convincing the community is a different deal. And so having this team, I think, will really show the community, okay, this thing is legit and this value is what it is.
So in your tweet, you said that this new data could be announced as soon as the January AAS meeting. That's a regular astronomers meeting. When in January is that this year?
So that is January 13th. So that's next week this time. And yeah,
that might be the date that this episode goes live.
So that might be today. Yes.
We might have to do a follow-up if big news happens. Okay.
Right. But yeah, and I've heard from their team that I haven't heard what the result is, but I heard that it will be coming out. So I'm very excited.
Great. All right. Moving on to the second entry on this list. It's the TD Cosmo milestone lensing paper. All right. Tell us what TD Cosmo is, Dan.
Yeah. TD Cosmo is the biggest international collaboration that tries to use this technique called strong lensing, looking at how galaxies and groups of galaxies can bend light. And this is an effect explained by general relativity. And when light is bent, it's not only kind of bent spatially, the time gets dilated. And by measuring how much time gets dilated, you could then infer the expansion rate of the universe. So it's a fairly involved mathematical technique, and you need to do a lot of modeling about how this light is getting bent. It's extremely neat to see these pictures of how galaxies are bending light, but it's a direct measurement of the expansion rate of the universe itself. And TD Cosmo is really the main team doing this.
Is this the same technique that like the Holy Cow collaboration uses?
Yes. So Holy Cow has evolved into TD Cosmo. So Holy Cow combined with some other groups, and they're now called TD Cosmo. So,
I should just add for the listeners that Holy Cow is some sort of perverse acronym. I don't know exact. Do you know what it stands for, Dan?
The whole part, that's H naught, the H naught that we referred to. L is lensing, and then I lose.
Yeah. I forget how ridiculous our naming conventions are in this field. All right. So when are we gonna hear about the TD Cosmo results?
Right. So they've had this interesting history to themselves where when they were known as Holy Cow, they came out and they said, we measured that the value of the Hubble constant is 74 or so, a high value. Mm-hmm. And I think that kind of the Hubble tension really kicked into high gear when they came out with that result. And then 2 or 3 years ago, they said, hold on a second. We've kind of been assuming fairly standard things about properties of galaxies, but what if we rip away all those assumptions and just use our own data, no external data, to constrain those assumptions themselves? And when they opened up that box, their values of the Hubble constant moved all over the place, and they kind of took themselves out of the game, I'd say, for a little bit. And
so they didn't necessarily disagree with the high values. It's just their uncertainties after opening up these options got much, much larger. Okay.
Yeah, they said you do it one way, you get a high value of the Hubble constant. Another way, you get a low value. We're not sure. So to try to keep things constrained just ourselves, we need to get our own data from like the James Webb Space Telescope. Really state-of-the-art data. And over the last 2 or 3 years, they've been getting that data. And if I follow the breadcrumbs, what I think that they've been finding is that things about the galaxies that they assumed originally were correct, but they are trying to put all this together in what they call a milestone paper, and everything that they've learned over the last 2 or 3 years, and have a new kind of final H0 result, and that's supposed to come out in the next month or so, from what I hear.
Next month. Wow. Okay, that's great. Okay, so that's 1 and 2. Let's go on to number 3. And this is the Dark Energy Survey's Year 6 final analysis. So tell us about this.
Right. So
tell us what the Dark Energy Survey is.
Yeah. So Dark Energy Survey is using a telescope in Chile, a really world-class telescope. And they are one of the preeminent surveys that try to do a number of cosmological techniques like measuring supernovae, measuring strong lensing that we just talked about, measuring another kind of lensing called weak lensing, where you're looking kind of in aggregate how much galaxies bend light, and try to do all these different cosmological techniques to measure a number of cosmological parameters. And I think they're one of the main surveys. They're pushing our field into what I'd call survey mode, where you have this giant telescope that is just taking pictures of large swaths of the sky every night and then just collecting an enormous treasure trove of data, and then has these really big teams across the world that are trying to analyze it. And they stopped taking data. They took data over 6 years. They stopped taking data a few years ago, and they're right now in the middle of doing one of their biggest analyses. It's called their Y6 3x2, where the 3x2 is combining a number of different techniques to make one cosmological measurement, really based on the technique called weak lensing, where you're looking in aggregate about how much light is bent by thousands and millions of galaxies to try to figure out the structure and composition of the universe.
So what kind of cosmological parameters or other kind of cosmological questions can the dark energy survey address or measure better than anyone else?
Right. So the dark energy survey, kind of in its namesake, is trying to measure dark energy, and will do that as well as anyone else. But the other parameter that it can do really well is what's called S8 or sigma 8. It's really a description of how clumpy the universe is on this specific scale. And by measuring the clumpiness of the universe, that tells you how the universe has evolved and grown up. And a lot of times in cosmology, there's these parameters that are a little bit arbitrary, but they're kind of chosen like to be meeting points for different techniques, where you could say, well, I measure this at this value and you measure at this. And, what that was chosen of what to measure is not as important, of just that multiple different techniques can measure it. So we could see, are we getting the same number? So this clumpiness is one of these important meeting points in cosmology.
When you say clumpiness, you mean in the distribution of matter in the universe. Like
exactly.
How is the matter distributed in a smoother or clumpier way?
That's right.
Yeah.
That's right.
Good.
Yeah. And previously, a number of surveys that tried to measure the clumpiness of the universe, they found a smaller value than what was predicted using measurements of the cosmic microwave background and the prediction of using our standard model. So same kind of story as with the Hubble constant. And a lot of people got excited that this was like number 2 for tensions, that it's not just this Hubble tension, it's its own thing. Maybe people are wrong, but that there's tensions popping up all over the place. And maybe these two things are related.
Good. So I have to admit, I've always been a little confused by the sigma 8 tension, not by the science of it, but like why it kind of rose to the level of impact that it did. It was never very statistically significant, right? It could just be a random fluke.
Yes. And that's, I think, what it's seeming like, that it was hitting this like 3 sigma level. So kind of still in the, I don't know, fluky possible thing. And it was seen more by one team than other teams. And the trend line seems to be like it's disappearing, but there's still a number of people that think it's real. And I think that this next DS paper will kind of cement how real it is.
We find out if it's real or not finally. Yeah. So you said that the sigma 8 tension maybe reached like 3 sigma or standard deviations of significance. That's the sort of thing that happens, a fraction of 1% of the time if you just look at a random data set. In contrast, what's the statistical significance presently of the Hubble tension?
Right. So the Hubble tension using the latest SHU's measurement is just over 6 sigma.
Yeah. Okay. So that's a lot more statistically significant. Oh, much, much less likely just to be some statistical fluke. Almost impossible to be.
That's correct.
All right. So let's go on to number 4 on your list. And those are the next data release cosmology results from the Atacama Cosmology Telescope, or what we call ACT. All right. Tell us about ACT and what it's going to reveal to us in this year.
Right. So far, what I've talked about is kind of these different tensions where these different surveys are measuring how the universe looks now, and then they're comparing it to measures the universe very young combined with a model. But so another interesting place to look at what could be causing these tensions is these measurements of the universe when it's very young. And the next kind of big one that's coming this year is from the Atacama Cosmology Telescope. So this is based in the Atacama Desert, and they are making kind of the most pristine measurement of how the universe looked like shortly after the time of the Big Bang. And this is not their first release. And in their last release, they saw a number of interesting things. And like we were talking about with kind of possible flukes, it's a lot of people are waiting to see were those things flukes or not, specifically because some of those things that they saw would also explain these other tensions. And it seems like a possible interesting coincidence that they saw some strange things in their data that just so happened to explain these tensions.
So some of the leading ways that we measure the cosmic microwave background are with satellite-based missions like Planck, and before that, WMAP and COBE. So, but this is a ground-based telescope. So what are the advantages and disadvantages of measuring the CMB, the cosmic microwave background, from space or from the ground?
Right. Great question. So yeah, so the leading measurement beforehand was Planck, and still the Planck satellite will dominate for certain what we call modes. It's amount of sky that you can cover, and what the Atacama Cosmology Telescope can do is kind of really focus in on small parts of the sky for long periods of time. So have very high signal to noise at very high resolution for very small parts of the sky. And a lot of the interesting physics would be when you could really kind of lock in on small parts of the sky and try to look at these small fluctuations on small scales. Now, at the same time, what I think some Planck people would say is, well, they're doing this from Chile, and from the ground, you have pollution and dust and all these things that get referred to as systematic. So another things that are harder. So when Atacama measures things that are possibly interesting, Planck would say, hold on a second, those might just be systematics. Your measurements are much harder.
Yeah. Okay. So doing things from the ground is perilous, but you can maybe make a higher resolution map, getting those very small temperature fluctuations of the cosmic background and the smallest scales, measure it better than you can do from space. Yeah, but it's tricky.
Exactly. So one of the most exciting things that they saw in their last release is at the level of 3 sigma significance of what we're calling early dark energy, that there's this other kind of dark energy that just popped up at the time of the cosmic microwave background. And what's particularly interesting about that is it's the perfect thing to also solve the Hubble tension. Because if you inject this little bit of energy and you propagate that forward, then you would get a higher value of the Hubble constant and everyone would be happy. Now, the couple things that are difficult about it is that you then be saying, hey, there's just this weird kind of dark energy that just pops up at this very specific time. And you're starting to deal with kind of fine-tuning type problems. And then the second thing is that actually measuring that signal is in the same place as all the kind of systematics that you're worried about from a ground-based telescope. So what I hear is if they're able to solve these systematics, then they have so much data that if that signal is real, it would be at the 6 or 7 sigma significance. So if they can beat those systematics, the amount of data really will show this tremendously well if this is real. So this could be a very exciting result, depending on how things shake out.
So I as a theorist, I'll just add my vision of this from my community's perspective, and I think it just mimics what you just said. We look at these theories that have been proposed involving early dark energy to explain the Hubble tension, or for that matter, this ACT data. And the theories look pretty baroque and ugly and have a bunch of weird parameters and they're complicated. And so we're skeptical going into it. But if the data get good enough, that will overcome the skepticism. If the data get compelling, we could be dragged into accepting this stuff to be true. The regular, ordinary dark energy wasn't exactly something theorists were comfortable with. Before we had data proving it was there. So the same thing could happen a second time.
Right. And I'd be curious what you think, because the biggest pushback I hear about measurements of the Hubble constant is this phrase, I'll never believe an experimental result unless there's a good theory that can explain it. And there's not, for all these things that I'm talking about, they're not great theories. They're what you'd call, I think, baroque. And I think
who's saying that?
I hear that all the time.
Really? That feels so backwards.
To me, I totally agree. To me, it feels backwards. And as an experimentalist, I can't stand it, but I hear it constantly.
I suspect those people are deliberately trying to be provocative and maybe a little tongue-in-cheek. Yeah. So, let me put it in a slightly less, provocative way. You should have some priors. You should have some idea of what you think is plausible and implausible. And then data should move your posteriors, your conclusions about facts. But if I really think a particular theory just couldn't possibly be true, it has a 0.00001% chance of being true, it would take a lot of data to convince me it's real. But if some other theory looks really plausible and like even likely to be true, maybe it would take a lot less data to convince me that's true. Like that sounds pretty rational to me. That's just good old Bayesian reasoning.
Right.
Statistical nuance, yeah.
Yeah, what I find is that people's prior on Lambda CDM is extremely strong. And trying to say, hey, there's possibly something that's wrong with it is hard for a lot of people to accept.
And when we say Lambda CDM, that's our nomenclature for like the standard cosmological model that's been in place since the 1990s or so.
Right.
Late 1990s.
And when we say
early
prior, we mean like the weight we kind of give to a theory because we think it's probably true, right?
Well, the odds that we think something is true before having data about it.
Right.
Prior to having data on it.
What's always a little strange to me is that in this standard model, we have dark energy and dark matter, neither of which we really understand particularly well. So to just say I will not budge from thinking that this is right, but I don't really understand its main components, I've always found a little odd.
Well, but I would say in the history of cosmology, people did say that about dark matter and dark energy. They said, I'm not going to accept this unless like the data is overwhelming. And then the data got overwhelming and they accepted it. You know, we can be won over. You can get me still, Dan. All right. Just keep at it.
Yeah, that's why I'm here on your podcast, just trying to convince you.
All right. So also with the Atacama Cosmology Telescope, there's some other things it's going to measure too that aren't related to these tensions. What should we keep our eye out for there?
Right. So the most interesting thing from my perspective, the other thing that we'll measure is it's called FNL. It's a characterization about the Gaussianity of the universe when it's very young. And really what that's telling you about is how did inflation work in that first fraction of a fraction or a fraction of a second. There's still, I think, it's hard to pin down the right theory for inflation, and the current experimental constraints have not been strong. And from what I hear, I think this will be an interesting constraint on what inflation could be.
So let me try to unpack that a little bit. So when we look at like the distribution of hot and cold spots in the cosmological background, they look like they're distributed following what we call a normal distribution, a Gaussian distribution. Like there's a, if you plot this bell curve, that reflects the distribution of these temperatures. But it's possible in some theories of inflation, so this theory where the universe grew really fast, really early on, that they wouldn't be shaped like a bell curve. It would have a different shape, especially way out on the tails of that bell curve. And the ACT telescope is trying to, measure that if it exists or put constraints on it if it doesn't. Is that about right?
Yeah, you nailed it.
Good. So inflation, of course, is like one of the biggest questions in cosmology. It really like sets the table for the whole future of the universe. It maybe even has things to do with, is there a multiverse, and all sorts of huge implications. There's a lot of kind of, not, primary, but like kind of secondary evidence for inflation. There are a lot of reasons cosmologists think inflation probably happened, but nothing that I would call a smoking gun yet. But maybe something like this could put it over that line.
Right. Yeah, that's the hope for where we're getting close to, is some kind of smoking gun.
All right. So let's go on the list further. Now we're on to number 5 of 7. And this is the DESI results, or at least some of the DESI results, the year 3 results. So tell us about DESI and what it does and what it's going to tell us this year.
Right. So I would say that DESI in the last year had the most exciting and puzzling result. So DESI is measuring baryon acoustic oscillations. So that's a feature of the universe from the time of the cosmic background, but kind of watching it propagate through the history of the universe and seeing how kind of this scale of waves at the beginning of the universe change over time, and they could constrain the universe's expansion. And what we kind of expected was that what they could do really well is measure the properties of dark energy. So the DE in DESI is dark energy. That's a dark energy spectroscopic experiment. And what everyone expected that they would find is that dark energy is consistent with what we think in the Standard Model, what we call it is the cosmological constant. So this is like a vacuum energy of space that Einstein originally proposed that still theory struggles with, but generally accepted. And
we talked about this with Sean Carroll on a recent episode of the podcast.
Yeah, that was great. And what they found is, again, kind of at this 3 sigma level, that maybe the amount of dark energy, its property, is changing with time, which was a giant surprise. And what's also interesting is that that's with baryon acoustic oscillations, and then with supernovae, which I work on, we've been seeing those same hints over the last couple of years. And when you combine supernovae with baryon acoustic oscillations, this significance starts to grow. And this is getting a lot of attention now, that maybe dark energy isn't what we thought it was.
There's a lot of other weird stuff with the DESI results from last year, though, right? The more I read that paper, the more I go, like, whoa, what's up with this? Like, none of these things line up right.
That's right. So one of the other kind of things that's gotten very popular is that if you try to constrain the mass of neutrinos, which has to be a positive number, like there has to be something there.
There's no such thing as negative mass.
There's no such thing, but their data favors that. Now,
yeah.
From what I understand, that result and this changing dark energy result actually are very much related. There's something interesting in their data, and possibly this is systematics, but the kind of word on the street always about baryon acoustic oscillations is that it's the most systematic free of any cosmological measurement. Just supernova, we have to worry about understanding how they explode. Baryon acoustic oscillations, you're just measuring redshifts of galaxies. It's as like straightforward as it gets. So now to say, hey, there's something wrong, no one has said it over the last decade or so.
So, okay, 3 possibilities. Either it is a statistical fluke and it all just goes away when we have more data, or it's, some systematic uncertainty that we haven't figured out yet. But like you said, baryon acoustic oscillations are supposed to be pretty simple that way. Or third, we're fitting this to the wrong cosmological model. And, the standard cosmological model doesn't work. Lambda CDM doesn't work. And we need to add something or change something in that model to make it all hold together.
That's right. And what's great about this year 3 is they just have so much data that if that dark energy evolution signal is real, it'll cross 5 sigma. So that will be impossible to ignore. And from what I also hear is that they're not seeing any systematics in their analysis. So we're going to know one way or another this year. And the data's already in the can. They're analyzing it now and should be out in 6 months or so.
6 months. Okay. So we're now most of the way through the list, and we're in the second half or roughly of 2025. Okay. All right. Great. Moving on to number 6. I know nothing about this one. DBAS ZTF? I've literally never heard of it.
Right. So these are 2 supernova surveys. DBAS, again, just
DBAS.
Yeah, it's like it's supposed to be like an I Love You Man movie reference. And ZTF, Zwicky Transient Factory. And this is kind of the flip side of this DESI story. So the DESI is seeing this signal for evolving dark energy, and when they combine with supernovae, it gets stronger. But supernovae, they use some data that's kind of quite old in terms of measuring the local universe, and that's been known for a while. And now we have data from these newer surveys that's trying to measure all these explosions that happen in galaxies nearby, and this will kind of replace the challenging part of the supernova measurement. So if that dark energy signal is real, this would confirm it or help it go away. So this is kind of the supernova side of, is there something funky going on with dark energy?
Great. All right, so I think that brings us to our 7th and final entry on this list. So this is all about a mission called Euclid. So before we even get into what Euclid's going to measure or release, tell us what Euclid is.
Right. So Euclid is a space telescope that was launched and led by a large European consortium. And they will do a number of techniques, but predominantly trying to measure the weak lensing of galaxies, like what the Dark Energy Survey does, and also trying to understand the large-scale structure, kind of how galaxies are distributed. So, like, they'll measure the clumpiness of galaxies extremely well. And going into space allows you to really understand how matter is bending light, and why you want to go into space is that our atmosphere will do similar effects. And the Dark Energy Survey has to come up with all these amazing algorithms to understand the impact of the atmosphere. But once you're in space, it gets a lot easier. So Euclid was launched last year. It flew out, and it now has a lot of data. And hopefully by the end of this year, they'll release the data in their first cosmology constraints.
That's great. So you said you think this will happen late in the year?
Late in the year, I hope. So,
okay.
Yeah, it is
this
very
might be in our 2026 January 1st episode.
Yeah, this is my last for a reason. But yeah, so it's the level that they're pushing to of measuring how much light gets bent. It's really beyond what anyone has measured before. And while some things get easier in space, there's a lot of other weird things in space of little asteroids or things hitting your telescope, or how your sun hits it. So I think that there's been some surprises that team has found. Seems like they've gotten things under control, but it is not a simple measurement. But if they can kind of beat all that stuff away, it's really, really pristine.
All right. So if I look back on this list, I see a couple of themes emerging. First of all, there are several cosmological tensions out there. Hubble tension certainly being the most prevalent or prominent or whatever, the highest in significance and most attention, but some other ones too. And it sounds like in the course of this year, we're going to learn a lot about some of these, or maybe all of these. The situation might get cleaner and better understood if things start to align. They might get even messier, but at least we'll learn things and hopefully make progress. And then also just, we continue to live in this age of precision cosmology where we're measuring these things at previously unimaginable, precision and resolution. That's really exciting to see. And now I want to ask, what things, if I went around and asked a bunch of other cosmologists, who, maybe don't work on exactly the things you work on, whatever, what stuff would they likely say they would put on their own list that maybe we haven't talked about today? Like, maybe we don't have to be as exact with some of those, but like what kind of things maybe aren't on your radar that our fellow colleagues in the broader cosmological community might be thinking about?
Right. Yeah. Great question. I think that one thing that was not so much on my radar and got popular and then kind of people stopped talking about, but I think will get popular again, is the question of when did the first galaxies form? And so this was a really big result that first came out of the James Webb Space Telescope, that they're finding all these galaxies that were born much sooner in the history of the universe than any of the models expected. And then it kind of came out that, well, possibly some of the measurements weren't quite right, but also the models were quite hard too. And galaxy formation is very hard. But now there'll be these big census papers of all these very old galaxies. And I think for a kind of big section of astronomy, where kind of astronomy and cosmology overlap a lot, that will be very exciting.
Yeah, I agree. That will get a lot of attention, as did the first Webb results. Will these measurements be fully spectroscopic? Will we really nail the redshifts?
Yeah, right. And I think that's exactly a thing. When the first set came out, there's like it was more photometric redshifts than spectroscopics, and then those redshifts were hard, and people got excited, and then people got not excited, and I think the next round will be kind of, mostly spectroscopic. You know exactly what you're getting.
So maybe this is yet another tension that we'll expect some clarity from this year.
That's right. That's right.
All right.
Yeah.
So I'm excited to be a cosmologist. I'm excited for 2025. And it's been great having you on, Dan. Thanks for coming on Why This Universe, and have a good year.
Thank you so much. It's a pleasure talking to both of you.
Why This Universe is produced and edited by me, Shalma Wegsman, and our co-host is Dan Hooper. Dan is a professor of physics at the University of Wisconsin-Madison and the director of the Wisconsin IceCube Particle Astrophysics Center. If you like our show and you want to support us, you can join us for as little as $3 a month on Patreon. There you can also get access to exclusive Ask Us Anything segments where you can directly ask Dan and I any of your questions on physics or whatever else. And to find that, just go to patreon.com/whythisuniverse. As always, thanks for listening.